This session we'll look at drawing the graphs of reciprocal trig functions. First of all, can you have a go at the starter questions? The first one revises some Year 13 work, the second one Year 12 work, and the third one you might want to use your calculator for. Here are the mark schemes. Okay, so we start off by remembering the graphs of sine, cosine and tangent and identifying key properties of these. So have a go at completing this table. The terms domain and range will be used when you're doing functions in Year 13, but don't worry about them. The domain is just what x values can you put in, and the range is what y values do you end up getting out. The period is the width of the repeating bit. So you know your trig functions just keep repeating, they have periodicity, okay, and it's just how wide that bit is. Here are the answers. Okay, so we're going to use that to help us with drawing our reciprocal trig functions. Remember which one is which, so look at the third letter, so you can see, remember sec, third letter C, so this is 1 over cos. And cosec is 1 over sine, and cot is 1 over tan, and because tan is sine over cos, the reciprocal of that would be cos over sine. So there are lots of different things that can help you sketch the graphs of reciprocal trig functions, but I'm going to use the one that seems to be most useful, especially if you're asked to do this in exams. So we're going to use the basic function to begin with. So I'm going to switch to drawing some graphs. So here we're starting with the graph of y equals cos x. So we're going to draw the reciprocal graph for that. So 1 over cos x is sec x. Okay, we start off by focusing on key features and important moments on your cos graph and think about the reciprocals there. So exciting things happen every pi over 2, don't they, if we're working in radians. Let's start with x is 0. We can see that cos is 1 and 1 over 1 is 1. So sec is going to be 1 as well. So wherever cos is 1, sec is going to be 1. Okay. Similarly, wherever cos is negative 1, the reciprocal of negative 1 is also negative 1. So sec is going to be negative 1 there. Right, the other exciting moments happen at the roots where cos is 0. If you are taking the reciprocal of 0, 1 divided by 0 heads towards infinity. So you're going to get an asymptote at that point. I hope you're better at drawing straight lines than I am. So I'm going to sketch in the asymptotes wherever cos is 0. Just pop those in. Okay, and then finally we're going to look at when cos is positive and when it's negative. So when cos is positive, the reciprocal will also be positive, sec will be positive. So that means the bit of the asymptote we'll be looking at will be the positive bit. Okay, here cos is negative, so the reciprocal is also negative, so we're interested in the negative part of the asymptote. Okay, and I'll just do that for the beginning as well. Right, now finally we join up the bits we know. So we join up from the asymptote to the 1 and it curves back up again. So then hopefully you can see that our red graph, which is the graph of sec of x, is made up of some kind of U shapes and some N shapes. Okay, right, oh, I can fit one in there. Right then, so I'm going to do the same for cosec, which if you remember, cosec of x is 1 over sine x. So we start from the graph of sine x. Now I'm going to just draw this without talking and see if you can predict what I'm doing. See if you can think through, what am I doing? Okay. Okay, so in order to draw y as cosec of x, we start with y as sine of x, and then we think 1 over each value. We look at the important values. So first we look at all the maxima for sine, which is 1, and 1 over 1 is 1, so we plot those points. Then all the minima, and 1 over minus 1 is still minus 1, so we plot those points. Then the other exciting things that happen are that the sine graph crosses the x-axis. When sine is 0, we're doing 1 divided by 0, so we get an asymptote. So we fill those in. And then we check where sine is positive, cosec will also be positive. So we want to be using the positive end of the asymptote. Where sine is negative, cosec will also be negative. So we want to use the negative end of the asymptote. And finally, we join it up and we end up with another bunch of u's and n shapes. And you can see that if you translate cos x, pi over 2, you get to sine x. So if you translate sec x, pi over 2, then you will also get to cosec x. Okay, so as you may expect, the tan graph is a bit different from sine and cosine, so the cot graph is also going to be a little bit different. Okay, so I'm just going to jot down here that we're going to do y is cot of x, which is the same as 1 over tan x, okay, which we could have is cos x over sine x. Okay, I'm going to draw myself a little triangle because that's going to help me think in a moment. So I've got my angle on the x-axis. Okay, right, we start off as before with exciting values. Now we know that exciting values are happening at all the multiples of pi over 2. But we also used for the other one where the graph was 1 because 1 over 1 is 1. Now I know that tan is 1 at 45 degrees or pi over 4. So that means every kind of multiple of pi over 4, then the cot graph is going to meet the tan graph. Okay, and similarly every time tan is negative 1, okay, then the cot graph is going to cross the tan graph. Okay, so that happens, we can see here we've got a nice y-axis, but even if you don't, you can remember it's at 45 degrees or pi over 4, minus pi over 4. Right, so now we're going to look at the exciting value. So let's look at when tan is 0. We know that we're going to have asymptotes. Wherever tan is 0, we draw an asymptote ready for cot because 1 divided by 0 is undefined. Shoots off to infinity. So that happens on every multiple of pi. Luckily, you can speed this up when you're watching the video by skipping ahead. Goodness me, that took a while. Right, now the other exciting thing on the tan graph is that you have asymptotes. Let's think about when those asymptotes happen. So you know that tan is opposite over adjacent. And the asymptotes happen when that adjacent is 0. But if we're doing adjacent over opposite for cot, that happens when adjacent is 0. 0 divided by anything is just 0. So wherever there is an asymptote for tan, there's going to be a 0 value for cot. Okay, so I'm going to just plot those points. Okay, and then lastly we're going to think about which bit of asymptote we want. So when tan is positive, cot will also be positive. Okay, so we'll be interested in the positive end of the asymptote. When tan is negative, cot will also be negative. So we're interested in the negative end of the asymptote, and so on. Okay. Right, and now finally we can join up the points that we've worked out. I hope you're smoother at doing this than I am. Try very hard not to let your asymptote curl backwards. It should obviously be an asymptote, but and get close to the graph gets close to the asymptote, but you don't want it to accidentally curl away from the asymptote. So this one is a bit busy to look at when you can see the tan graph as well, but the cot graph is the red graph, which is a bit like a kind of back to front tan graph. Okay, right. Okay, so in isolation, here is the graph of sec x, and hopefully you can see that these key features make sense. You have got a period in the cos graph of a total of 2 pi, so you can go from 0 to 2 pi, and that section repeats all the time. So it's exactly the same for sec x, the period is exactly the same. You are not allowed x values where the asymptotes are, so that means the domain, the set of possible x values, is everything except odd multiples of pi over 2. And the range, the set of y values allowed, is everything except this middle bit between -1 and 1. Okay, right, so use those features. Which one of these statements is correct for the points on the graph A, B, C and D? You should get this one. And which graph is sec? Remember, which is the reciprocal of sec? I usually use one value like x is 0 to help me work it out, and this is the one you should pick. D. Similarly, we have very similar properties for the cosec graph. Okay. Another thing to notice is that if you translate the sec graph, you get the cosec graph. So here we are, this is my wobbly sketch of cos x and y is sec x. And then if we translate those pi over 2 to the right, so in the positive x direction, that's the same as replacing x with x minus pi over 2. So sec of x minus pi over 2 lands exactly on top of cosec x. So they're the same. Okay. Which key features are correct? Which statement is correct for these points? Here's the answer. Which is the correct graph for cosec? D again. And here are your properties for cotangent. Remember, the period for tan is just pi, not 2 pi. It's just pi. So the period for cotan will also be pi. Okay, here's some key points, A, B, C and D. Which statement is correct? This one. Which graph is the graph of cot? You might have picked A, which would, I think, would say that was fine as well. The reason I picked C was I thought it more clearly went through pi over 4 and 1. Right, now, thinking back to those graphs and their properties, see if you can complete the table. Remember, the domain is just all the possible x's you're allowed, and the range is the y's that you end up with. Okay, here are the answers. There we go. You may notice some different patterns. For example, within each row, the domain, the values you're not allowed in the domain are the same as the asymptotes. Between a function and its reciprocal function, the roots of the original function match up to the asymptotes of the reciprocal function. Okay, and then also the possible y values you can get, they're the same between tan and cotangent. If you look at the cos and the sec one, the values of cos that are allowed, that you end up with, the y values, are basically all the ones you're not allowed for sec, except for -1 and 1 themselves. And the same with sine, you get between -1 and 1, so cosec is going to be everything except the ones in between -1 and 1, but you are allowed -1 and 1. Right, hopefully you're getting familiar now. See if you can match them up. Here's the answer. Okay, and here are the values of x and the values of y that you get. Which one of these is 1 over sine? So you're thinking about the shape and where it is placed. It should be C. Sec is 1 over which one? And then think about which values you would end up with. Okay, which one of these is the correct one for tan? Has the correct period, etc.? It's B. Okay, which graph is this one? It's one of the new ones, and you need to choose which. It's cosec. This time we want to simplify this, so we know we've got some kind of translation. Very sensible option would be to sketch the graph on your calculator of y equals sine 90 plus theta. Make sure you're in your radians or degrees. This graph shows radians, annoyingly, but never mind. Okay, so this is the graph you end up with. Notice there's an asymptote at x is 0. So that tells us it must be either cosec or sec, because sine is 0 there. Cosec or minus cosec. Right, let's have a look here. We can see that we've got negative values between 0 and pi, or 0 and 180. But cosec itself is usually positive there because sine's positive there. So that tells us we must have negative cosec. Right, now, slightly trickier. We've got lots of options here. I'm really hoping you can easily match up graph A. Okay, and familiar to you should be graph B now. Now, graph C is a bit trickier. We can see it looks kind of like a squashed version of the sine graph, so we might be thinking, the period's only pi, so it's half of what it should be, so I think it's been stretched. So that would think sine of 2x. But sine of anything goes between -1 and 1, and this goes between 0 and 1. So it's not going to be sine of 2x. The inverse graphs we haven't even considered, and it doesn't look weird, so we'll stick with these ones. Sine of sine x sounds awful, so let's try sine squared x. Let's imagine squaring the numbers here, the y values here. If we square 0, we get 0. If we square 1, we get 1. If we square 0, we get 0. If we square -1, we get +1. We're going to get only positive values. So in fact, graph C is sine squared x. Let's try this example. Okay, the first part is using your transformation knowledge from year 12 and applying it to reciprocal trig functions. So we've replaced x with 2x, so we know it's happened in the x direction. In fact, we've multiplied x by 2. Multiplication tells us we have a stretch, an x direction. It will go opposite to what we think. We have a stretch scale factor 1 over 2. Okay, you could check it by sketching it on your calculator. If we've stretched scale factor 1/2, then the period, which is about the width, will also have squashed, will have stretched by 1/2. So the original period of sec x was 2 pi, and so the period of sec 2x is just going to be pi. We half it. Okay, and then we're asked to sketch the graph. I would do this on your calculator. We go into your calculator. We want to have sec of 2x, which is 1 over cos x. So I've typed that in. I'm going to make sure I'm in radians because that's what the question wants. So set up and go down to radians. That's good. Okay, and I'm going to draw it. Right, now that's good. When we get to part C, it wanted a graph between 0 and pi. So I'm going to do view window, and I'm going to make my x go from 0 up to pi. Okay, the rest of it seemed all right, so we'll sketch that. Okay, and this is what it looks like. Let's have a go back to the answer here. There's our graph. So notice that they have labelled the 1 and the -1 because those are important y values for your maximum and minimum. And they've labelled where the asymptotes go at pi over 4 and 3 pi over 4. So they made it really clear. So we've done, the period is definitely a pi, and we've sketched the graph. Part D, state the values of k such that sec 2x equals k has no solutions. We've got the graph of y equals 2x, sec 2x, so we need to sketch the graph of y equals k. That'll be horizontal, you can see here. Now, if that k is anything between -1 and 1, you can see it doesn't cross the graph of y equals sec 2x, so that means you'd have no solutions. So it's that in-betweeny bit, -1 up to 1. Here's some questions for you to try. You may want to do the first one and then think, does that help you with the second one? What's changed? What stays the same? You may be able to predict your answer for question 2 and then check that you've got it right. If you haven't, see, that'll give you a surprise, make you think a bit harder. If you've got it right, hopefully that helps reveal to you a property or an aspect of the graphs that you have learnt about. And then try that again, predicting for question 3 and 4 and 5. Question 6, you may want to use your calculator, and question 7, similar to the one we just did. Here are the answers. And here's a last extension question. Your calculator could help with this. Here's one approach. So it looks like a sine graph that's been moved up, so it must be C. Well done.